All right. Now we would like to talk some skills to improve the matching properties for current mirror layout. From the very beginning, you will see this is the most fundamental one. We have two transistors exactly the same in size. How can you match their properties after fabrication? This is some kind of very simple layout. Yeah, every transistor has its own layout pattern here and there. You can see they don't have any kind of common centroid layout pattern. It means after fabrication, you need to face some kind of systematic and random mismatch. However, for this paper, we will only like to focus on systematic mismatch instead of the random one. For a random mismatch, the only way to handle it is to increase the layout areas for both. That's it. To simplify the analysis, in this paper, we would like to only focus on first order gradient. First order means linear. Gradient means systematic mismatch. All right, this is some kind of model to simulate the first order systematic mismatch. According to two-dimensional random systematic mismatch, you will see this is some kind of vector point to the maximum gradient error, and then this is the angle. Yeah, that's it. To get better layout mismatching cancellation, we have this. For example, 1221, we call it interdigitized type 1. Uh, Along with the interdigitization, we have 1221. It means it also has common centroid layout requirement. And how about the other one? We have only 1212. It means according to dispersion, this type 2 is better than type 1. However, as I mentioned, for the five golden rules, common centroid is the top one. It means you had better follow, you had better fit the common centroid layout requirement than all the others. Anyway, anyhow, according to the five golden rule, you will see the type 1 has common centroid layout pattern and the type 2 doesn't. So it really means after fabrication, the performance of type 1 should be much, much better than type 2. And these are only some kind of one-dimensional layout pattern. Let's go for the two-dimensional one. So we have 1221. Yeah, it is also common centroid, but we can make it even better. Why? Because according to the schematic, you can see the sources of both M1 and M2 are connected. It means we can flip, for example, the second row to make all sources in the middle, just like this. Then, never mind, it belongs to M1 or M2. According to the schematic, they can be connected. It means they can be overlapped because they share the same node, right? So in this way, you will see they are almost the same for the layout pattern. However, for common centroid type 2, it has better compactness. It means they fit all the same layout rules for common centroid. But for type 2, actually, it has better compactness. So it means what? After fabrication, the performance for common centroid type 2 should be a little bit better than type 1 because, again, it has better compactness. And then Professor Geiger and his students would like to do some kind of gradient modeling. As I mentioned, only for two-dimensional linear one. I mean first order one, just like this. And they would like to do such kind of easy calculation. You can see for equivalent threshold voltage, that is the most important one. Usually, you need to do such kind of double integration all around the area they occupy. For VT1 or VT2, you need to do such kind of double integration. And then divide it by the effective area. That is the average threshold voltage for each subdevice, this or that. Pay attention to the layout. When we are talking about threshold voltage, it all belongs to the channel. I told you already, channel is the king. And for all the others, they are only supporting characters. So focus only on the integration of the channel area, just like this and that. And forget about the others to simplify the derivation. So anyway, anyhow, according to some kind of hardworking of Professor Geiger's students, they have some kind of approximation expression for VT1 and VT2. You can see according to such kind of linear model, linear gradient model, VT1 got this, VT2 got that, you will see they are not the same. Because for VT1, it has the minus term, and for VT2, it has the positive term. So they are not the same. And it means after fabrication, you need to face a lot of systematic mismatch. Okay, to make it better, as I mentioned, we have such kind of one-dimensional interdiscretized type 1 and type 2. For type 1, you will see D1 and D1. It means for M1, it has the first and the first. Okay, so it has VT1 and VT4 connected in parallel. So you can sum them up, sum VT1 and VT4 up to get the total value for M1. Congratulations. For what? You will see we have minus this term and positive that term. They are exactly the same. So according to positive, negative terms, they can cancel each other to make the perfect result. Yeah, it means what? For first order gradient, VT1 plus VT2 can cancel each other perfectly. So we call it first order gradient cancellation. And how about M2? M2 actually is composed of VT2 and VT3, right? D2, D2, blah, blah, blah. So again, you can see if you sum up VT2 and VT3 for M2, again, the second term can be cancelled perfectly. Bingo. However, if you have a look at interdiscretized type 2, the story is not the same. For M1, actually, it is composed of VT1 and VT3. So we have VT1 plus VT3 for M1. Don't tell me, this is minus, that is positive, they can cancel each other. Sorry for that. Please have a look at the coefficient for M1 this term. For W, you have 3/4. But for VT3, you have only 1/4. So it means what? They cannot cancel each other perfectly. And it means after fabrication, M1 still needs to face the impact of the first order gradient. Similar condition for M2 because it is composed of VT2 and VT4. So again, if you sum them up, they cannot cancel each other perfectly. Yeah, anyway, anyhow, yeah, you can do such kind of easy calculation by yourself and then figure out M1 and M2 are not exactly the same according to such kind of first order gradient impact. And how about the two-dimensional common centroid type 1 and type 2? You can see they have exactly the same pattern as I mentioned moments ago. However, the only difference is type 2 get better compactness than type 1. It means what? All the spatial coefficients are smaller for type 2 than type 1. You can see this and that. Yeah, type 1 is larger than type 2. That's it. That's it. The magnitude of the coefficients are larger for type 1 than type 2, but they share exactly the same equations, just like this. Okay, then we can have a detailed look at for each transistor. For M1, you will see this and that. It is composed of VT1 and VT4. Also, please have a look VT1 VT4 minus positive exactly the same coefficient, so they can cancel each other. Positive, negative, again cancel each other. Perfect cancellation for this pattern. Okay, not only for M1 but also for M2. M2 is composed of VT2 and VT3. You can see they can cancel each other perfectly. So again, what is the difference between type 1 and type 2? Very, very simple. Yeah, it means the coefficient. Okay, here or there, DH or D, VDS, blah, blah, blah. For such kind of coefficient, type 1 is larger than type 2. So it means after fabrication, the impact for type 1 will be a little bit more than type 2 because it has larger coefficients. That's it. Okay? Then let's go for the MATLAB simulation provided by Professor Geiger and his students. Totally, we have how many patterns to be simulated? 5, right? But if you have a look at this, you will see why there seems to have only 3 characteristic curves. Why? Simply because for the other 3, they are quite small. They are quite close to 0. Okay, so for your vision impact, there are only 3 curves, but actually there are 5. To make a clear picture for you, allow me to zoom in this one by 2 orders. Okay, then you will see clearly there are 3 other curves instead of only 1. Anyway, anyhow, allow me to point out which get the worst impact from the gradient arrow. The blue line, right? And who is blue line? Let's go back to C, the simplest one, the simple layout. It is the silliest one. It's the most stupid one because you don't try any kind of effort to match them. Just let it be. It's really stupid. And for stupid layout, you can only get the worst impact. You will get the maximum error according to gradient mismatch. Okay? Then who gets the second worst? Anyway, anyhow, without common sense, just think, which also doesn't have common sense layout requirement. This one, right? Into digitized type 2 because you have 1, 2, 1, 2. Even though its dispersion is better than type 1. However, according to the 5 golden rules, I warn you again and again, they have priorities. The first rule, common centroid, gets the highest priority. Don't make any mistake. You need to fit the first, and then, if possible, to fit the second or the third. Don't say that I would like to fit the second or the third, but I will violate the first. Sorry for that. If you do something like this, you will get much worse impact from systematic mismatch. Okay, so allow me to show you. If you compare into these types, type 1 and type 2, again, type 1 fits common centroid layout requirement, but according to dispersion, it is worse than type 2, right? For type 2, it doesn't fit the common centroid requirement, but it gets better dispersion. So let's wait and see. Which one? I mean, common centroid or dispersion gets the more impact than the others. Okay, let's have a look at this. For common centroid type 1, yeah, sorry. For allow me to, okay, for interdistinct type 1 and type 2, let's have a look at the simulation result. Which one is for interdistinct type 2? Where? Oh, the red one. See, this is for interdistinct type 2 without common centroid layout. The magnitude is some percent, yeah, larger than 2% in mismatch. And how about the type 1? Interdistinct type 1. See, the maximum is only 0.30%. So for mismatch, actually, type 1 is two older than type 2, right? See? So it is a golden proof for all of you. For interdistinct type 1, it fits common centroid layout pattern requirement, but the dispersion is worse than type 2. On the contrary, for interdistinct type 2, it has better dispersion but violate the common centroid layout requirement. So what is the consequence? You can see the performance for type 1 is much better, two order better than type 2. So again, it means what? The requirement for common centroid is much higher than dispersion or all the others. What is the others? We have compactness, we have chirality, blah blah blah, all of them. All of them has much less impact than common centroid. So please keep this in mind. According to the help of this golden proof, the simulation result, the big difference between interdistinct type 1 and type 2. Please pay attention. For 5 golden rules, the first gets the highest priority. If you can fit it, then consider to fit the second. If you can fit the first and the second, then go further to fit the third, the fourth, the fifth. Don't reverse the order. Don't fit the second, the third, or the first. But forget about the first rule. It doesn't make any sense. Please keep this in mind. This is a very important proof for you. Then let's have a look at common centroid type 1 and type 2. They belong to two-dimensional layout pattern. Let's have a look the impact between all the difference between the two-dimensional layout pattern and the four-dimensional one. Look, yeah, this is only for 1D. Okay, even though for type 1, it fits the common centroid layout requirement, but it has only one-dimensional layout pattern. Let's have a look at the two-dimensional one. What? You can see. According to the simulation, the two-dimensional common centroid type 1 and type 2 both has less, I cannot say much less, but they still have less impact from mismatch. Okay, so again, it shows you two-dimensional layout pattern is better than one-dimensional. Okay, so try your very best, not only to fit the common centroid layout requirement, but also to increase the symmetry. Yeah, you can see type 1 interdigitized type 1 is only for 1D, right? And for common centroid type 1 and type 2, they are both two-dimensional. So the more symmetry, the better. It is a good proof again for you. 我们刚刚很快的跟各位 highlight 一下，就是说，如果你去看 interdistinct type one and type two 那个是 1D 的啦一维的那个布局，然后type one 事实上它有符合同重心，但是它的散度比较差。那 type two 呢没有符合同重心但是它的散度比较好。结果你看它们两个的误差差了108000里，差了100倍，所以这个再次跟各位验证我当初在跟大家谈的5大对称性的要求，事实上呢第一个 rule 就是 common centroid， 你要做同重心布局嘛，它的重要性远远高于2、3、4、5。那同样的道理，第二条的重要性远远高于3、4、5，所以各位一定要想尽各种办法，先符合第一条的同重心的要求，再去符合第二条对称性。如果对称性你符合完了之后，再去考虑第三条那个dispersion 散度，巴拉巴拉巴拉。那有关散度呢？各位可以看一下有关对称性事实上，这个是把原来这一张图里面趋近于零的这个部分把它放大给各位看。还有3条线吗？不是你脸上挂3条线是说我把那3条趋近于零的线放大100倍给各位看你还是可以分出中间的那个差距因为这个2维的 Type 1跟 Type 2。有没有？这里是2维的那边只有1维的嘛？2维的对称性比1维的高，结果各位就会发现，这个做出来的那个结果，2维确实比1维好，所以它又验证另外一件事那个对称性也是蛮重要的。如果你有办法增加对称性，那么你做出来的效果就一定会比较好。Okay, let's go further. How to enhance the symmetry? Professor Geiger and his student created some kind of innovative but also crazy idea. You can see, compare with the original one, this or that. You can see the symmetry is doubled. Why? Because according to the, how can I say, to such kind of square layout, you have 1, 2, 3, and 4. You have 4 symmetrical axes. Okay, if you go back to see the original one, never mind for type 1 or type 2, you have only 1 and 2. Sorry, okay, 1 and 2. That's it. Okay. According to symmetry, later I will explain, never mind symmetry or anti-symmetry. Both make sense. Only asymmetry doesn't make any sense. 我在讲对称轴的时候我会提到正对称跟反对称，待会儿会再做更详细的说明正对称跟反对称都 OK 只有非对称没有对称是不 OK 的那个在下一篇论文会跟各位再做比较仔细的那个说明。Okay, anyway, anyhow, right now we have totally 8 subtransistors. So for M1, it gets VT1, VT3, VT5, and VT7. So if you sum up VT1, VT3, VT5, and VT7, you can see, all these terms will be cancelled by each other. Also this one and that one. Anyway, anyhow, okay. You have you can calculate it by yourself. Anyway, anyhow, I would like to tell you after summation, VT1, 3, 5, 7 for M1 and VT2, 4, right? VT2, VT4, VT6, and VT8. You will see the result for M1 and M2 will be exactly the same. Then let's go for real simulation result. It will even more convincing. Okay, so allow me to overlap the simulation result of the new layout pattern along with the original one. Please keep in mind we have three zoomed in curves for simulation, right? Now we have the first, the new one. Okay, so totally we will have four curves here. And again, you will see for the new one, it is very close to zero. So allow me to help you zoom in again for how many orders? Again, for extra two orders. So here you can see they are at -2 order and here -1. Wow, wow. You will see again to enhance the symmetry. The symmetrical axes for those two are only two, right? We double it to make four symmetrical axes, and then the result is enhanced by two order. It means the mismatch error is reduced by 100 times. Wow, bingo. That's it. Okay. To make it even better, oh, this is a very good proof for the power of symmetry. Again, I highlighted already the better symmetry. The more symmetry, the better result. Okay, so here is some kind of summary. You will see for a simple layout, actually it's quite bad. All right, but for the others, you will see for common century type 1, type 2, or even for the most innovative one, the 4-segment common century layout, according to all the simulation result, it gets the minimum error and achieve the best accuracy. It is reported that it can achieve something like 18 bits in accuracy. Wow, it's really amazing and fantastic. However, as I always warn you again and again, nothing is free. You need to pay for it. What kind of price you need to pay for such kind of very high accuracy layout pattern? The chip area, the layout area. If you go back to see the layout pattern here, for example, the W is 100 micron for both M1 and M2. So divided by 4, okay? It means for each sub-device, the width is 25 microns. 25 microns here, 25 microns here. So for each edge, the width is larger than 50 microns. And also, it is the same for the other side. So totally, the area you need to sacrifice for such kind of high accuracy layout pattern is much larger than 50 squared micrometers squared. Okay, so totally much larger. Why I told you much larger? Because 25 here, 25 micron there, you still need to sacrifice extra length for the spacing, right? So totally you need to sacrifice more than 2,500 micron squared. That is a huge price. Would you like to pay for it? It's up to you. I don't know. OK， 这个代价这样子实在是太高了啊！以100 micron 宽度的那个 M1 跟 M2 来讲啊，我刚刚有解释过了，你要浪费掉可能远远超过2500 micrometer squared 这么大的面积，你愿意付出吗？我想大部分人都不愿意吧。所以等一下我们会给各位另外一个选择。Later I will show you another even better solution to enhance the symmetry. Okay, without such kind of aerial wasting layout pattern. 啊，这个太浪费面积了。Okay, let's go further. Anyway, before I introduce the other paper from the same group, allow me to show you that Professor Geiger and his students would like to reduce the layout pattern, the layout area for you. Okay, this is another innovation. You can see all the sources, uh, all the sources are the same, right? And then all the gates are connected. I mean for M1 and M2. So the only difference is D1, D1, D2, D2. Wow. That's according to symmetry and common centroid requirement, it is quite similar to this, right? But you can see D1, D1, D2, D2. Okay, but there is a big difference according to the gate and the source. Yeah, please use your own eyes as cameras. Here is the layout pattern for common centroid type 2. Then let's come here for comparison. Again, the source and the gates are totally connected for M1 and M2. The only separated region is the drain, right? So equivalently, allow me to show you the equivalent schematic. It looks like this. You have D1 here, D2 there, then the gate is the same. The source is also the same. Okay, that's it. Gate here, source there. Then we have D1 and D2. Yeah, that is the equivalent symbol for this layout. But in theory, you can see in theory, okay, instead of in practice, yeah, you can see it look like you have separate D1 here, D2 there, but you connect their gate all together and also connect their source. That is for equivalent. Okay? Yeah. Anyway, why Professor Geiger and his student would like to propose such kind of strange layout pattern? The only thinking is to reduce the overall layout area. You can try it by yourself. I promise you. With the same W over L, this layout pattern will require a little bit less area than the original one. I mean, than this. Okay? Do it by yourself. But why? Simply because the smaller area. Oh, okay. Oh, I mentioned already. The more compactness, the better performance. Okay, yeah. Then this is another very good point for you. I need to show you. According to mismatch, we have two kinds, right? One is random mismatch, the other one is systematic mismatch, or you can call it deterministic mismatch, the same. Okay, yeah, and have a look at such kind of uh, horizontal axis. Actually, if you go in reverse direction, it means the layout area will be increased. All right. So how can you handle random mismatch? According to the red line, the larger area, the smaller mismatch. However, for systematic mismatch, it is on the contrary. The larger area means that the spatial coefficients will become larger, right? So the impact will also be enlarged. That's it. It means to please everybody means please nobody. You cannot please both. You cannot please random mismatch and then systematic mismatch. If you would like to reduce random mismatch, you need to enlarge the area, but you will also increase the impact of systematic mismatch. According to statistic theory, if they are uncorrelated. I mean, random mismatch and systematic mismatch. If they are uncorrelated, then the overall variance will become the summation of the individual variances. So you can see this, for example, for random, and that is for systematic mismatch. Then the overall mismatch needs to consider both, right? The summation of the variances. So again, the final one will look like a smiling curve. For each layout pattern, you need to figure out, in theory, the minimum, all right, to consider both, to take random and systematic mismatch into consideration. That's it. That is what I need to warn you again. You cannot only focus on random or systematic. No, 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 no. You need to consider both. Then allow me to show you this. According to spatial effect, you will see this, the blue line for the waffle structure. I mean for the new one, the crazy one. All right. And how about the red one? For the original common centroid type 2. That is also for two-dimensional layout patterns. All right. You can see according to the coefficients, blue line is usually less than red line. Okay, so it means the new waffle structure is smaller in coefficients than the two-dimensional common centroid layout pattern. After simulation for the mismatch, you will see the waffle one gets less impact for such kind of systematic mismatch. Okay, to make it even better, I mean to make this layout size even smaller than the waffle one, Professor Geiger and his students also created such kind of even more weird structures for layout. 你看起來足詭異嘅就對啦哈。不過伊嘅layout面積會變較細。Anyway, anyhow, they provide us 1, 2, 3, the other 3 pattern. Yeah, and after simulation, according to their smaller layout area requirement, you will see all of them have better performance. Please pay attention to this. Minus fifth power of 10. One order less, right? One order less than this one. Bingo. That's it. Anyway, what is the conclusion for this paper? Yeah. First of all, innovation is the most important issue for you guys. I mean, for analog IC design or analog IC layout engineers, the most important issue is to be creative, innovative. IQ actually is not so important here. All right. So if you are not so smart, you need to do hard working. Yeah, for compensation. 勤能补拙了哈。巧的人是有好处了，但是你类比 IC 设计也是布局哈。巧无讲足重要的啦，通重要就是要有创意啦，巧的人是不是一定就创意？真歹讲，非常歹讲。OK， 所以你若无人较巧，不要紧，勤能补拙，你较拍拼的就好哈。All right. For the same series, they published another paper called nth order circular symmetry, blah, blah, blah. Anyway, anyhow, I wouldn't like to talk about it because sometime later, they proposed the other one, much, much better than this. And they prove the next paper will be much better than this. So you don't need to learn this not so important paper at all. Allow me to show you to the end of the chapter the best from the same series of paper published for layout pattern generation. That is the best of the best from the same group, from the same library in Iowa State University. Yeah. Again, you can see my very good friend, Professor Randall Geiger. Then De Gang Chen, one of his colleagues for cooperation, and for all the others are their students. This is the best of the serious papers for layout pattern generation. Okay, let's have a detailed look at it. So what I would like to tell you is, for example, from the sorry, I forgot to mention that even though this is the best of the best, it can be only applied for two devices. Okay, to match two devices to any kind of order you like. Okay, never mind for first order cancellation or second order, third order, first order, as you like. And from MediaTek, they required at least second order gradient cancellation. Keep this in mind. But you can make it even better than the requirement of MediaTek when necessary, all right? So for two devices, we call it A and B from the beginning. That is the simplest layout. It violates the common centroid requirement, right? How can you help it to fit the common centroid requirement? Very simple. You can flip it to the right, I mean horizontally or vertically, okay? But according to such kind of flipping or mirroring, 你要做近射了哈，或是翻转了，水平、垂直都可以。You need to make sure the new pattern needs to be different from the original one. If they are different, I promise you, you will increase the gradient cancellation by one order. Okay? So from the very beginning, they don't have common centroid. It means they have zero order gradient cancellation capability. How can you help them cancel the first order one? Okay, no worries. Just mirror the original pattern horizontally or vertically, but you need to apply symmetry or anti-symmetry. The only rule is to generate a new pattern different from the older one. So, for example, if you would like to mirror it horizontally, right now, you need to have symmetry, right? Symmetrical mirroring, because B becomes B, A becomes A, and BA is different from AB. If you move back the new block BA back to the original one, you will see BA is different from AB. That's it. That is the definition. If you have the wrong mirroring, for example, if you apply anti-symmetrical mirroring here, then B will become A, and then A will become B. That is the definition for anti-symmetry. Then the original one is AB. The new one is still AB. Sorry, wrong mirroring. Got it? 我头来讲足清楚，恁听有吼？我意思是讲啥？你不管要安做垂直啊、水平的翻转还是叫做近射啊，好啦吼，你会使用正对称，你会使用负对称。正对称是啥？像这个啦吼，像这个物件你甲看吼，水平翻转 B 变成 B，A 变成 A，你就家己人嘛，所以这个叫做正对称啦。反之呢，你会使用逆对称、负对称吼 ，B 变成 A， 然后 A。变成 B， 不过不幸的代志发生啊吼，因为原来叫做 AB， 你用逆对称了，伊嘛是叫做 AB， 歹势，安尼就无才讲吼，你袂使安尼做就对哦。不管你用正对称还是用负对称吼，咱的黄金铁律就是讲，你翻转了，你对称你甲正射了，你新产生的迄个布局样态一定要甲原来不相共。 但是你毋通得到一个错误认知，你讲啊，安尼讲的意思就是讲，咱一定用正对称 B 变 B，A 对 A，A 我听你咧把握，不是安尼意思啦哈。Okay, don't get any kind of misunderstanding. According to the two examples I showed you moments ago, here, if you apply symmetrical mirroring, you will generate new different one. Okay, but if you apply anti-symmetrical mirroring, B becomes A becomes B. Oh, the new one will be the same as the original one, so you cannot enhance the gradient cancellation capability. Don't get any kind of misunderstanding, a fast generalization or a fast conclusion that you can only apply symmetrical mirroring instead of anti-symmetrical mirroring. No. The conclusion, the first conclusion here is totally wrong. Allow me to show you another very good example. The same block A and B, but you would like to mirror it vertically. Now you need to apply anti-symmetry, right? A becomes B, B becomes A. So it means BA is different from AB. You can increase the gradient error cancellation from zeroth order to first order. Congratulations. However, if you do wrong mirroring, I mean, if you apply symmetrical mirroring vertically, then A becomes A, B becomes B. Sorry, AB is the same as the original one. That is the wrong mirroring. Got it? You can see for this, you need to apply symmetrical mirroring. Okay, symmetry. And for that, you need to apply anti-symmetry. So just make it by yourself. Never mind for horizontal or vertical mirrorings. Keep this in mind. You need to apply the correct one. To apply symmetry or anti-symmetry for mirroring, all right, to generate new block different from the old one. That's it. 所以不管你要安怎变，你要安怎请半变，正对称跟逆对称，你一定要用了对。不管你是水平翻转还是垂直翻转，反正啊，你就跟其中的一个，不管是正对称啊、逆对称，你都是生出来新的迄个布局样态，一定要甲旧的不相共，安尼就对啊。好，咱继续甲看落去哈。So you can see, for this one, okay, we generated here, yeah, with horizontal mirroring, right? You can see the original AB with symmetrical mirroring. You get BA configurations. You get ABBA. Now, ABBA, if you would like to mirror it again horizontally, what kind of symmetry you need to apply? Sorry, right now you cannot apply symmetrical mirroring again. No, you need to apply anti-symmetry because A becomes B, B becomes A, and A becomes B. You can see the new one, BAAB, is different from the original ABBA. Okay, if you apply symmetrical mirroring again, then sorry for that, you will get ABBA, which is exactly the same as the original one. It doesn't make any sense. Got it? You allow me to move it back. Yeah. See? That is the newly generated block. For comparison, is it different or the same with the original one? You can move it back, overlapped with the original one. You will see, the original one, you have blue here, but you have purple for the new one. You have purple, then blue for the new, blah, blah, blah. So they are not the same. Congratulations. You make one more order for gradient cancellation with correct mirroring. Got it? Okay, let's go further. For the same ABBA, if you would like to mirror it horizontally, you need to apply anti-symmetry, right? And how about to mirror it vertically? Again, A needs to become B. B needs to become A, right? So again, you need to apply anti-symmetry. All right. And for this one here, if you would like to, it is the same, right? If you would like to flip it horizontally, then again you need to apply anti-symmetry. A becomes B, B becomes A. However, for the same block here, right? They are the same, right? If you would like to flip it vertically, then you need to apply what? Symmetry instead of anti-symmetry. B becomes B, A becomes A. If you move back the newly generated block, you will see BAAB, ABBA won't be the same as the original one. ABBA, BAAB. That's it. So you can do it again and again. I mean, according to mirroring symmetry, you can apply symmetry or anti-symmetry vertically or horizontally to generate new but different blocks. Then you can go further again and again. Finally, allow me to show you fact patterns from Professor Geiger's group. A, B, C, D, and E. Wow! For E, actually, you can cancel. Oh, okay. Yeah. You can see for this one, you can cancel up to the first order, right? And how about B? Correct mirroring, second order, third order, fourth order, and finally for E, fifth order. Then F and G actually, they are related to such kind of circular symmetry pattern I mentioned moments ago. And I also told you that you don't need to learn it because for this paper, moments later, we will show you the new pattern is much better than the older ones, not only for accuracy, but also the layout area is much less than the circular one. Okay, so you don't need to learn old and also bad layout patterns. They doesn't make any sense. All right. But I'm going to show you the simulation result from A, B, C, D all the way to E. You can see, wow. Okay, for E, it can cancel not only the first, the second, the third, the fourth, the fifth. Okay. After simulation, you can see all the result becomes zero for the first order gradient all the way to fifth order. And how about the circular symmetry pattern F and G? You can see for F, it can only cancel up to the third. For G, it can only cancel up to the second order gradient. But have a look at this. You need to waste a lot of area for layout. Okay? Okay, not only for F but also for G. See? A lot of area needs to be wasted. And how about our new layout pattern? They are very compact from A, B, C, D all the way to E. You can see for all of A and B, they are laid out side by side without such kind of extra area to be wasted. So for compactness, our A, B, C, D, E all the way are much better than F and G. It means the area, the required layout area will be much less than all the others. I mean, with the same order of gradient to be cancelled. Okay, that is the end of this chapter. And also, it finished the good layout patterns for MOSFETs. We spent 2 chapters for those, right? 2 chapters means a lot. For all the others, I wouldn't like to spend more than 1 chapter. That is too lengthy. But for MOSFET, that is the most important device for our IC layout. And this is the reason why I need to spend 2 chapters for their layout. Since after, you can learn new skills by yourself. But how? You can get online for Googling or to search through IEEE Explorer database. Yeah, if you are lucky, you can find some new layout papers. Then read it by yourself. Thank you.